Okay, now we proceed with the discussion of power series. Okay, so in the previous discussion, we were able to be introduced to the concept of approximating functions by Taylor polynomials. Okay, so we were able to find out that we can actually approximate the values of functions using what we call Taylor polynomials. Okay, so for example, we can write out the first up to the fifth order of fifth degree Maclaurin polynomial for e raised to x. Okay. And then we also have been able to discuss that the higher the degree or the higher the order of the approximating polynomial, the better the approximation becomes. Okay. Now, here what we are going to do is to really have the function written off in terms of a polynomial of a series of a polynomial of a series in polynomial. Okay. And what the big idea behind is that if we actually add up infinite number of terms, sorry, mali pala yung ano ito. If we add up infinite number of terms of your Taylor or Maclaurin polynomial, okay, we could actually make your we could actually make your sum converge to that function. Okay. So in the next two lessons, we will see the several important types of that function, including f of x, x, e raised to x can be represented exactly. That's the key word here. Okay, the exact representation of a function. Okay, by an infinite series, which we will consider now as power series. Okay. Um, the power series, we call this as a power series because it basically is a series, okay, in terms of the powers of x. Okay, it is a series in terms of the power of x. As you can see here, that's x raised to this is x raised to 0, x raised to 1, x squared, x cubed, up to x raised to 1, and so on. So these are powers of x. Okay. So that is why we call them power series. Okay. And again, this is the exact representation can only be achieved by adding infinite number of terms. Okay. If we add infinite number of terms, we will be able to get an exact representation. Supposedly, we will be able to get an exact representation of your function. We can make it converge to or sum up to that function. Okay. So we'll do some preliminary work by defining some terms related to the power series. And then later on we should be able to write out um, representations of your functions in terms of this power series. So let's define a power series. Um, if x is a variable, then an infinite series of the form of this one, okay, is called a power series. So we are calling this a power series mainly because this is a series in terms of the powers of x. Okay, this is a series in terms of the powers of x, so that's why they are called power series. Okay, so more generally, an infinite series of the form written this way is called a power series centered at C. Okay, so this is a power series centered at 0, and this is a power series centered at a certain number C. So we agree. We agree that the symbol x minus c raised to 0 is 1. Okay, even if x equals c. Okay, we'll agree to that symbol because basically that's technically that should be an indeterminate form. Okay, that should have been 0 raised to 0. But we will agree just to have a more simplified notation. And mathematically, this is also a more convenient way of doing this. That we will agree that this symbol is still holds true if x equals c. Okay. So wala din naman siyang there will be no harm there in terms of its mathematical meaning. Okay, when we use this definition. Okay. Um, so we in example 44, we illustrate some of the infinite series. Okay. we illustrate some of the infinite series that are considered to be power series. Okay. So say for example, x raised to n over n factorial. Okay. Its sum from n equals 0 up to infinity has this expansion. Okay. So 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on. Okay. The series negative 1 raised to n times x plus 1 raised to n from n equals 0 up to infinity, okay, would be expanded in this manner. And remember that since your x, okay, has a term added to it, okay, it means that the center of this is at negative 1. Remember that the general form is x minus c. So if that becomes x plus 1, okay, that means x minus negative 1. So therefore, the center is at negative 1. Okay. So when the center is at 1, okay, we have this series, such as this one. Okay. So these are some of the examples of the power series that we can write out. Okay. So there. Um, we will define another concept related to the infinite power series. Okay. Um, as the radius and interval of convergence. Okay. So a power series in x can be viewed as a function of x, such as this one. Okay, so which means that we have a power series on the right side, which is equal to a certain function f of x. Okay, where the domain of f is the set of all x for which the power series converges. Okay, so which means that we can only have function values, okay, for f, okay, for all those x where the power series converges. Okay, so which means that the domain of x is dependent on where the power series will converge. So that is why it is important for us to actually determine where the power series would converge, and that is what we would like to discuss it here. Okay, that is what we would like to discuss here. Okay, the determination of the power series, of the domain of the power series, is the primary concern in this section. Of course, every power series, okay, converges at its center. Okay. So automatically, the center of the power series is contained within the interval of convergence, or what we call the domain of your power series, and consequently of f also. So the center is automatically included in the domain of the power series. Um, the reason for that is that all power series would converge at the center. Okay. You have to remember that point. All power series would converge at its center. And its proof is this one. Okay. If you actually substitute C, okay, to your function, okay, which will have this one, okay, it would have a value of AO. Okay, so it means that your power series would converge when x equals C. Okay, it would have a sum, which is AO. So therefore, this center is always included in the domain. Okay, so C always lie in the domain of F. Now, the following theorem states that the domain of a power series can take three basic forms. Okay, it can either have a single point, okay, an interval centered at C, or the entire real line. So the possibilities for the domain of your power series is illustrated here in figure 13. So it's either that your domain, okay, would only have a single point. It would be within a certain interval centered at C. Okay. It would be the entire real line. Okay. So these are the possibilities. Okay. And these possibilities are stated in theorem 20. Okay. The convergence of a power series. For a power series centered at C, precisely one of the following is true. Okay. Number one, the series converges only at C. So that's the first case. Okay. So the series converges only at C. Okay. Number two, there exists a real number R, positive R, okay, such that the series converges absolutely for x minus c less than r, okay, and diverges outside x minus c. Okay. So ito yung sa second stipulation. Okay. Um ito yung center ng ating this is the center of your your series. Okay. Then um in a certain interval, okay, there would be a number r for which from this up to this endpoint, okay, except at the endpoints, okay, except at the endpoints, and from here to here, okay, your power series will converge. Okay, ito yun. Inside that interval, your power series will converge. And outside that interval, this one, outside that interval, your power series will diverge. Okay, so that's the second possibility. Okay, the third one is that the series converges absolutely for all x. So it means that it covers the entire grid line. So this is Theorem 20, part 1. This is Theorem 20, part 2. And this is Theorem 20, part 3. So ito yung illustration. These are the illustrations of these points here. Now, the number r is what we will now call the radius of convergence. Okay. So there is this r, okay, in which measured from or counted from C up to a certain uh, a certain r. Okay. So a certain point where the maximum distance between that point and C is r. Okay. That is where your power series would converge. And outside that, here, outside that interval, your series would now diverge. Okay. So if the series converges only at C, we can consider the radius of convergence to be 0. Okay, because it just converges on a certain point. Okay. And if the series converges for all r, for all x, the radius of convergence is finite. I mean infinite. Okay. So which means that the range of your convergence is either 0 and infinity. So in between that, itong is number 2. So in this case, you have your r equals 0. The radius of convergence is 0. In this case, your radius of convergence is infinite. Okay. And in between, itong second point of theorem 20. Okay. This interval, okay, ito. The set of all values of x for which the power series converges is the interval of convergence of the power series. So where x converges, where your power series converges, will be included in the interval of convergence. So in here, we don't have an interval of convergence here because your series only converges on a single point. Here, this is the interval of your convergence. Right. Here, the entire number line is the interval of your convergence. Okay, so those are some of the definitions that we need to be clear of. Okay, so our task now is to find what is R. Okay, what is R? And what would be the interval of convergence? Let's call it IOC. Okay, para mas maganda. Okay, so let's say for example, let's find the radius convergence for this series. Okay, so number 1, we know that the center of the series is 0. Okay, because this is just simply x. Okay, if the center of that is other than 0, then it would have been x minus c, where c is a constant number. But since that c, we don't see it here, it means that c is equal to 0. So therefore, the center of your series is at 0. Okay, so if we actually substitute 0 here, we will be able to find a sum, okay, which is 1. Okay, and that means that you will be able to find that at x equals 0, your series n factorial times x raised to n converges to 1. Okay, so meron na tayong center. So this is the center of your this is the center of your series na. Okay, so there. Now, let us try to find out the radius of convergence using the ratio test. Using theorem 17. Okay, the limit imposed by Theorem 17. Okay. Because what we will try to find out is this. Um, we will try to find out what values of x will that converge. Okay. Remember the requirements of Theorem 17. Eh? The series will converge if if this ratio, if the limit of an plus 1 over an, as n approaches 0, is less than 1. Okay. If this ratio is less than 1, it would converge. Okay. Um, if it is greater than 1, or if it is infinite, the series will diverge. So trying out that one, we have an, ito pala, we have an is equal to n factorial over x raised to n. So an plus 1, the next term, or the succeeding term, is n plus 1 factorial times x raised to n plus 1. Okay. So if we take the ratio, we have here the um, x raised to n, n plus 1 factorial times x raised to n plus 1. Okay, that's your an plus 1. And then your an is n factorial times x raised to n. So we can actually cancel this answer, this two. What would be left is n plus 1. And we can cancel this two. What would be left is x. So we will have n plus 1 times x. That would be your, that would be what is left of it. Okay. Now, since we will be evaluating this now, we will be evaluating this as n approaches infinity. Any variable other than x, other than n, can actually be, what will happen here is this. The limit of the absolute value of n plus 1 multiplied to x as n approaches infinity can be written off as follows. We can write it as the limit of the absolute value of n plus 1. Okay. And since this is already positive, no, so we really need not to write not to write the n plus 1, the absolute value here, because n plus 1 is considered to be positive since n is is in the domain of positive integers. Actually, that's from 0 up to infinity, so that's positive. Okay. And then we'll multiply this by the limit of the absolute value of x as n approaches infinity. Okay. We would be able to evaluate the limit of this, but this automatically becomes absolute value of x because there's no n here. So therefore, this is a constant. For this limit, this is a constant. Okay, so therefore, this simply reduces to the absolute value of x times the limit of n plus 1 as n approaches infinity. Okay, but um, the thing is, so this is n plus 1 now. If we actually evaluate this limit, this becomes an infinite number. So therefore, this limit is an infinite number. Okay. It means that this series would converge nowhere. It would not converge anywhere except at its center. Okay. It would converge at this point, but outside that, it would not converge anymore. Okay. Because there's no value of there's no value of x. Okay. There's no value of x aside from x equals 0. Okay. Where it would converge, since the ratio test returns that this ratio is an infinite number. Okay, or the limit of this ratio is an infinite number. So that means that, again, the series would not converge anywhere except at x equals 0. Okay. So our conclusion is that the series therefore converges only at a single point, and that your radius of convergence is 0. So this is the conclusion that we will be able to get from there. Okay. All right. Next, let's find the radius of convergence for this series. Okay. We take note that this series is centered at x equals 2. Okay. We know that we take note that this series is centered at x equals 2. So therefore, at the minimum, okay, it is convergent at that point. So convergence dito. Okay. Now for x is less for outside that point. Okay. We test the series using the ratio test again. Okay. Ratio test works here because we're dealing with power series. So these are powers of x, and ratio test is the best way to test series that are convergent quickly, that converge quickly. such as power series. Okay? So that is why ratio test is the more convenient way of doing this. Okay, so we do it this way. We let a n as 3 times x minus 2 raised to n. So its succeeding term is 3 times x minus 2 raised to n plus 1. So we'll take the ratio, evaluate the limit, and see that its limit is x minus 2. Okay. So it implies that your limit is a finite number. Okay. So this limit is a finite number. And in that case, if that is a finite number, for your series to converge, the requirement for the ratio test is that that finite number must be less than, that finite number must be less than 1. That finite number must be less than 1. That's what that's what theorem 17 states. Okay. Since it ends up as a finite number, for a particular value of x now, this is a finite number. Okay. So, I hope you are able to get why this becomes x minus 2. Okay. Um, you can cancel 3 here, you can cancel this, and what is left of is x minus 2. There. Okay. So, and since there is no n here, for this limit, this number is a constant. So therefore, its limit is simply that constant. Okay. So, according to the ratio test, okay, that series that we are trying to test would converge if that finite number should have been less than 1. Let's evaluate this inequality now. Let's evaluate this inequality. X minus the absolute value of x minus 2 means it is or yeah this means that this essentially means that um your x minus 2 is less than 1. Okay. Or your x minus 2 is greater than negative 1. Okay. Since this is inside an absolute value, okay. Remember that your x minus 2, the absolute value of x minus 2 equals um, positive x minus 2. Okay. If x minus 2 is greater than positive. Okay. And it is negative x minus 2 if x minus 2 is negative. Okay, so but nevertheless this inequality translates to this. So it's either less than less than 1 siya. Okay, or greater than negative 1. Okay. So solving this for x, this is we'll add plus 2 here, so plus 2. So when x is 3 and your x is again this is plus 2 minus 2 plus 2 plus 2. So this is x greater than 1. Okay. So when your x is actually less than 3 but greater than 1, okay, your series would converge. So taking note that your series converges at x equals 2 automatically. Okay. We also know that your series would converge between 1 and 3. Okay, between 1 and 3. So here we don't really know if this endpoint x equals 1 and this endpoint x equals 3 are included. That's another matter that we will have to talk at a later section. Okay, but in this case, what we're sure of is that in between 1 and 3, in between 1 and 3, your series would converge. Okay, and as you can see here, the distance between this and this is the radius of your convergence. Okay, that is the radius of your convergence. So that is from here to here. That is the radius of your convergence. And that radius is actually equal to 1. Okay. That radius is actually equal to 1. Okay. So, again, your series would converge between, okay, your series would converge between 1 and 3. Okay. But we're not sure of if 1 and 3 themselves are included. Okay. What we're sure of as of now is that what we're really sure of as of now is between 1 and 3. Okay. Okay. Your series is convergent when x is between or is greater than 1 but less than 3. Okay. And that includes your center. Okay. So we know that in this interval, at least your series converges. So in that case, we were able to find the radius of convergence as 1. Okay, here, let's try to find the radius of convergence of this. Okay, so the center, it seems that the center of our series is at 0. Okay, so it converges now at x equals 0. Okay, now for x not equal to 0, okay, we use the ratio test. Okay, so we find the limit of this one, which this is your an plus 1. Okay, and this is the reciprocal of your an. This is the reciprocal of your an plus 1. Okay, this is your an plus 1, I mean, and this is the reciprocal of your an. Now, these two cancels each other out, leaving x squared. Okay, that's 3 minus 1 na lang. So that may iwan dyan is x squared. These two cancel themselves out. But what's left of are two factors, 2n plus 3 and 2n plus 2. Okay, if you are asking how that happened, remember that 2n plus 3 factorial is 2n plus 3 times 2n plus 2. Okay, times 2n plus 1 factorial. Now, this 2n plus 1 factorial and this 2n plus 1 factorial would cancel themselves out, leaving these two factors. Okay? So, yun. I hope that you were able to get a grasp of this definition of your factorial. Okay? So, continuing, okay, we would have x squared over 2n plus 3 over 2n plus 2 here. Okay, and that since this x is constant to this limit because you're evaluating the limit in terms of n. Okay, so you can take it out, treat that as a constant, so you will have x squared here. But this limit actually becomes 0. Okay, basically you can divide this with n squared, both the numerator and the denominator. That becomes 1 over n squared over 4 plus 10 over n plus 6 over n squared, which is 0, 0, 0. So that's 0 over 4. So this is 0. And therefore, by ratio test, that limit becomes 0. Now, since the limit is 0, your series is convergent. But we cannot really, we will not be able to solve a particular value of x for which it would converge. In fact, it would converge for all values of x. Okay. This means that if this limit becomes 0, this means that your series would converge entirely for all values of x. Okay. Because we will not be able to solve any particular x which it will diverge and it would converge. Okay. The fact that this limit is 0, okay, or is 0, that means that for all values of x, any values of x that you place here, okay, this series would converge. So therefore, the interval of convergence of this one is from negative infinity up to positive infinity. Okay, and that the radius of convergence is infinite. Okay, so we have here an example of 3 examples of the first stipulation of your theorem 20, wherein your series would only converge at a single point, okay, at the center. Okay. We have another example where you have a finite radius of convergence, so that is 2. Okay, that's the second stipulation of your theorem 20, and you have here the third stipulation of your theorem 20, in which your radius of convergence would be infinite, and that the entire real number line is your interval of convergence. Okay, but again, as I have pointed out in example 46, we haven't had yet theorem 20 is kind of silent about how the series would converge at endpoints. Okay. We don't have a problem with this one and this one because it's already settled that it only converges on a single point, okay, or it converges on the entire number line. Okay. But our problem is that what if R is finite? Okay. So we don't know if it converges, it diverges at the endpoints, both endpoints. It diverges at the lower endpoint, but converges at the right endpoint. Okay. It converges on the left endpoint, but diverges on the right endpoint, or it actually converges on both endpoints. Okay. So expanding on the possibilities of theorem 20, instead of actually specifying 3 possibilities, there are actually 6 possibilities for your convergence. So it's either this is stipulation 1 or stipulation 3 of theorem 20. Okay. This entire 4 possibilities are under stipulation 2, but the endpoints may or may not converge, or your series may or may not converge at the endpoints. Okay. So let's try to work on example 48 and demonstrate what this means. Okay. So let's find the radius of convergence of this power series. Okay. In which again by ratio test we will find that um your limit returns a finite number, okay, for a certain value of x. By the way, the center of this series is at 0. Okay. So we should actually you should take note of that always. Okay. Where the center of your series is. Okay. So here we consider now that your limit, the limit imposed by the ratio test, or the limit that is being asked by ratio test to be evaluated is um turns out to be a finite number for a value of x. Okay. And in that case, it seems that we can compute now um, an interval for which that this series would actually converge by imposing now a condition for your x. Okay, based on theorem 17. So this means that if this is x equals 0, okay, it's either your x is less than 1 or your x is greater than -1. Or in a more compact way, we can write your interval of convergence this way. Okay. So we will have it at -1 and +1. Okay. So what we're sure of is that sorry, here in this entire in this interval, your series converges. But what we're not really sure of yet is whether it converges on this endpoint, okay, on -1, okay, and it converges on +1 also. So we're not sure of if they converge. Okay, at the minimum, okay, we'll think of it this way. At the minimum, okay, this is where your series would converge at the minimum. Before we actually did the ratio test, we first say that at the minimum, your series is convergent here before the ratio test. After the ratio test, we expanded that minimum. So from this minimum convergence, from a minimum convergence here at this point, we now say that your series is convergent at least, okay, in this interval, okay, or at least within this interval. Okay. Now what we will try to find out now is whether it actually converges on the endpoints. And to do that, we will have to do actual test. Okay. So we will evaluate, okay, this series at -1 and +1, the endpoints. Okay. So at x equals -1, okay, your series becomes this. This is an alternating harmonic series. This is an alternating harmonic series. We know for a fact that your alternating harmonic series is convergent. Okay. We know that this is convergent. So it means that at this point, okay, at this point now, your series is now convergent. Now, we will redraw now your number line, okay, which would now include x equals -1, okay, into your convergence. Okay. So what we do not know yet is if it actually converge at +1. So we know that this is included in the interval of convergence. Okay. And now, at this point, at the minimum, our interval of convergence can be specified this way. At the minimum, after this step. Okay. However, for x equals 1, okay, at x equals 1, your series becomes this, okay, which is your standard harmonic series. This is a standard harmonic series, or the positive harmonic series, which is a divergent P-series. We know that this is a divergent by theorem 11. Okay. By theorem 11, this is a divergent series. So therefore, positive 1 is not included. The endpoint positive 1 is not included in the interval of um, convergence. So our final interval of convergence, okay, is -1. Okay. X, we notice that we place an equal sign here so that we say that -1 is included in the interval of convergence. But we also notice the absence of it on the other side because we say that positive 1 is not included in the interval of convergence. We can alternatively write this as this. Okay. With the understanding that a bracket represents, okay, inclusion of this endpoint, and and a parenthesis, okay, and a curved parenthesis indicates exclusion. So brackets indicate inclusion of endpoint. Anyway, this is something that you have discussed, that you were able to discuss in courses that dealt with sets. Okay. So when you were studying sets and inequalities, you were specifying your sets this way. Okay. So brackets indicating inclusion of endpoint, while this one, a curved parenthesis, okay, indicate exclusion of endpoint. Exclusion to to the interval of convergence. Okay. But you can simply write it this way. If this is something, if this is something that couples you, you can still write it this way. Okay. Graphically, you represent this one is represented using this notation. So you use a bracket to include -1 into the ano into the into the interval of convergence, and you use a curved parenthesis to indicate its exclusion. Okay. And by the way, from here, okay, from this graph, we were able to get that graph. Okay. From this graph, it seems that our radius of convergence is what? Okay. The radius of our convergence is what? Were we able to specify that? What? Here. So the radius of convergence is what? Okay. Even if kahit dito niyo siya i-measure, even if you measure it here, okay, still the radius of convergence is 1. Okay. Example 49. So we have here the radius of convergence of this alternating power series. Yeah. Okay. Oh yeah, this is the alternating power series. Okay, so we take note. Okay, we take note that your center is -1. So at this point, at the minimum, this is where your series converges at this point, at the minimum. Okay. Now we evaluate this limit and find that the limit equals a finite number for a value of x. Okay. So it's a finite number for a value of x. So in that case, we will use the condition for convergence under Theorem 17, okay, in which we will have that finite number to be less than 1 so that we will be able to say, that the series would converge, okay, and that we will be able to find out what values of x that series would actually converge. So it's either x plus 1 over 2 is less than 1 or x plus 1 over 2 is greater than negative 1. Yun yung ibig, this is its implication. The implication of this is this. Okay, so that means that your x plus 1 must be less than 2 or your x plus 1 must be greater than negative 2. And subtracting negative 1 on both sides, for both inequalities, you'll have x to be less than 1 or x to be greater than negative 3. Okay. So we'll adjust this now. We will adjust that to be to this to this number line. So starting at x equals negative 1, our radius of convergence, our interval of convergence now would include at least, okay, x equals negative 3. We don't know yet if this is indeed included, okay, and x equals 1. Okay, so x equals 1. Again, we don't know if this is included. Okay, what we're sure of is this, okay, and this is where your series converge. Okay, these are the values of x where your series would converge. And we would like to know if actually x equals negative 3 and x equals 1 is included. Okay, and by the way, before we proceed, from this, we will be able to deduce that your radius of convergence is 2. That's negative 3 minus negative 1, so that's 2. Okay, so that is your radius of convergence. Now, the last step is to actually determine whether the endpoints are included. Okay, so at x equals negative 3, okay, at x equals negative 3, okay, your series becomes the sum of negative 1 raised to n times x plus 1. So negative 3 plus 1 is negative 2. Negative 2 raised to n over 2 raised to n. 2 raised to n. Okay, for n equals 0, I think, yeah, n equals 0 up to infinity. Okay. So let's separate negative 1 here. Okay, let's separate negative 1 here and see that can be written as negative 1 times 2 raised to n, which can be written as negative 1 raised to n times 2 raised to n. Okay, so that becomes negative 1 raised to n, the original negative 1 raised to n, multiply that to this negative 1 raised to n, then multiply that to 2 raised to n, and then divide it with 2 raised to n. These two cancel themselves out to become 1. Okay. These two, since you have the same exponents, can multiply themselves, okay, and become positive 1 raised to n. So this now becomes summation of 1, okay, for n equals to 0 up to infinity, which we know to diverge. Okay. So it means that at this endpoint, your series is divergent. Okay, at this endpoint. Okay. Now how about at this endpoint? So let's have at x equals 1. Okay, your series becomes this. The sum of negative 1 raised to n multiplied to that's x plus 1. X plus 1. So 1 plus 1, that becomes 2 raised to n divided by 2 raised to n for n equals 0 up to infinity. These two factors cancel themselves out to become 1. Okay, so what is left of is the summation of negative 1 raised to n for n equals 0 up to infinity, which we know also to diverge. Okay, because that's simply 0, 1, 0, 1, 0, 1. And we don't know. This is an alternating series. Okay. This is an alternating series. And if this is an alternating series, there are two requirements for it to converge. Number one is that the succeeding term should be larger, should be smaller than the um, prior terms, which is obviously not the case. Okay, because if you're having it as 1, then -1, that decreased. But the next term, or the next term after that is 1. Okay, so that did not decrease. So from this pa lang, this requirement is not satisfied. Okay. And number 2 kasi is that the limit of an as n approaches infinity should be equal to 0, which is obviously not the case because your values are simply oscillating between 1 and -1. And so there is no chance that your um, function of the series would or the end term of this would become 0. So therefore, this is known to diverge under theorem 14. Okay. Alternating series test. It's 14. Okay. I hope you know why this would diverge because this is just simply 1 plus 1 plus 1 plus 1 plus 1 and so on. So it's an increasing sum. Okay. So therefore, this would diverge. So therefore, at the endpoints, at x equals 1, we also know that this series would also diverge. Okay. So it's divergent at both endpoints. So which means that um, your series is only convergent, okay, at this interval from -3 to +1, excluding the -3 and -1 themselves. So you can write or you can represent now or you can illustrate now this interval using this diagram. Okay, again, curve parenthesis represents the exclusion of the endpoints to the interval. This is now your IOC, final IOC. Okay, interval of convergence. Okay. So here, the curve parenthesis represents or represent the exclusion, okay, of your endpoints from the interval of convergence. Okay, so that's for example 49. Okay, so I would like you to work on example 50 and verify the findings here. Okay, would like you to work on example 50 and find the findings here because basically we're just following a certain pattern here. Okay, first you determine the center. Okay, because that's the first point where your series will converge. Number one. Number two, find R and the endpoints of your interval of convergence. So that's the minimum. Okay, and then find whether at the endpoints your your series would converge or diverge. Okay, so if they converge, include that in the minimum interval of convergence. Include them in the minimum interval of convergence. If they diverge, then exclude them. Okay, so I would like you to verify the findings here. For example, 50 on your own. Okay, and let us proceed with one of the most important things that I would like you to learn on this lesson. Okay, differentiation and integration of power series. Okay, so since we will be dealing with or in the next topic we will be using your power series as a method of solutions of method of solving ordinary differential equations. Okay. One part of the solution, okay, or one part of such solutions of such procedure is to actually differentiate your power series. So you need to learn how to differentiate and integrate power series. Okay. So power series representation of functions has played an important role in the development of calculus. In fact, much of Newton's work with differentiation and integration was done in the context of power series. Okay, especially his work with complicated algebraic functions and transcendental functions. Okay, so these are other mathematicians that use power series and the operations that come with them. Okay, uh, in their work. Okay, so once you have defined a function with a power series, it is natural for us to determine whether the function and its corresponding power series is continuous, differentiable, and so on. Okay, so this theorem would actually provide us a way on how to characterize them in terms of continuity, differentiability, and so on. Okay, so theorem 21 states that if f of x, okay, here written as a power series, okay, and that power series has a radius of convergence r, okay, and interval of convergence, okay, between this, okay, f is differentiable is and therefore continuous. Okay, so you can say that a power series is continuous within its interval of convergence. Where your power series is convergent, okay, that is where it is continuous and that is where it is differentiable. Okay, now this is its derivative. If you take the derivative of f, it becomes this one. It simply is applying the power formula in each of the terms. It actually, yung rules of differentiation is applied on each of the terms. Okay, so that is, for example, this is a constant. If you take the derivative of this that becomes 0. So you can see it here. Okay, while this term has a derivative of a1 because the derivative of x minus c is simply 1. Okay, this one will have 2 here. Okay, 2 a and a2 2a2, okay, and then x minus c, then 2 minus 1. So you'll have it here, okay, and so on, okay. But if you actually write it as a series, okay, if you actually write it in summation notation, it becomes this one. It simply you have it simply it can simply be written by again applying the usual power rule formula here by bringing down n here. You call it bring down. Okay, so we'll bring down n here. So that's n times an. It gets multiplied with the coefficient. And then x minus c raised to n gets to be subtracted by 1. But here is an important point that you have to see. The limits have changed. Okay, so the limits have been changed. So if you take the derivative, the limits of the summation actually will change. Okay, so that's how we take the derivative of your function in power series form. Okay, its antiderivative or its integral basically, okay, is of course the arbitrary constant is still there. Okay, plus you'd be basically applying the power formula here term by term. Okay, so starting sorry, not here pala, but here. Okay, because we have f of x here. Okay, so not here, dito pala. So you start here. Okay, so since that is a constant, okay, the integral of a0 dx is simply um, a0. But remember that here we are considering that your power series is centered around a certain number. So instead of just simply multiplying this with x, okay, you multiply it with x minus c. Okay. Again, that's a consideration that you have to remember because we are talking about a power series that is centered around a certain number. Okay, so that's it. Okay. And then you'll have for a1, okay, for a1, you'll add 1 to the exponent and then you divide 1 plus 1 here, so you'll have this one. Okay, and so on. But in the case of this term, the summation of an times x minus c raised to n for n equals 0 uh, plus infinity. Okay. Um, it means that it means that when you integrate something like this with respect to x, it means that you just simply have to add an exponent and this denominator. But this the limits does not get changed. Okay. Because basically, a0 here or n equals 0 here is still here. Okay. You still have to consider that a0, the presence of a0 in your integral. Okay. So that is why we not change the limit. Okay. Here kasi, your a0 disappears. Okay. Your a0 disappears. And so there is no need for us to consider that term, this term, okay, when n equals 0. That x raised to 0 is to be taken care of, is to be taken care of this thing. Okay. That has to be taken of n minus 1 then, when your n is equal to 1. Okay. Here kasi, the only way that we need to keep that, at n equals 0 is because of this, coefficient. But take note that you are adding a term here. When you are integrating, you are adding another term into your series. Okay, so that's how we get the derivative and antiderivative of your function in power series form. Okay, so the radius of convergence of the series obtained by differentiating or integrating a power series is the same as that of the original power series. Okay, so generally, the radius of convergence is constant for f of x, f prime of x, and the integral of f of x. Okay, in all of this, r is constant. Okay, but I o c, the interval of convergence, may be different. Okay, in this. Okay, the main difference is on the endpoints. So, the the endpoints the endpoints at each of this may actually be different from the original. Okay, so theorem 21, okay, states that in many ways, we'll talk about this in a later example. Okay, we'll talk about that in a later example. So theorem 21 states that in many ways, a function defined by a power series behaves like a polynomial. Yun naman yun. A power series actually is a polynomial, so they should behave as a polynomial. It is continuous in its interval of convergence, and both its derivative and its antiderivative can be determined by differentiating and integrating each term. Okay, that's the idea behind it. That's that term by term differentiation and integration, okay, of your power series. What might complicate this is the fact that we would like to write a more general a more general a general nth term, okay, an expression describing the nth term of the integral and the differential. I mean the derivative. Okay, so that's where the challenge is. But basically, differentiation and integration of a power series is nothing different than differentiating and integrating a polynomial, because basically a power series is a polynomial. And if you can wrap your heads around it, a polynomial is actually a power series. A polynomial is actually a power series. So if you have to for example, if you have to find the derivative, okay, if you find the derivative of this power series, you can perform term by term differentiation here. That is, the derivative of this is 0, the derivative of this is 1, the derivative of this is this. Okay, so you have to bring down 2. Okay, and then if you multiply this, that becomes x. Okay, and so on. If you multiply this here, if you get the derivative of this term, it becomes this, and so on. Okay. Now, if you actually simplify this, you'll get this one. Now, what do we get? Observe this and this. They are the same. Okay. They are the same. And if you take note, this is actually a power series that represents e raised to x. So what does this imply? It implies that whether you get the derivative of e raised to x as a function, okay, or as a power series, the results are the same. Okay. So whether you get the derivative of this e raised to x as a power series, you would have the same power series as its derivative. Okay, so that's the wonder of your e raised to x. That's the wonder of your exponential. Okay, let's consider this function. Okay, given by this one. Okay, and let us try to find the interval of convergence for the integral for its integral for the original function and its derivative. Okay, so its its derivative is given in this. Okay, remember that we have to take the derivative. If your f of x is the sum of x raised to n over n, for n equals 1 up to infinity, its derivative, okay, is it's 1. Its derivative is obtained by, again, bringing down n here. So that's summation of n times x raised to n over n. This is n, but this is n minus 1 already. But we will have this to be n equals 2. Okay, n infinity. Alright, so this simply becomes the sum of x raised to n minus 1 for n equals 2 up to infinity. Okay, so actually you can check it you can check it this way. Uh, if you expand this becomes x plus x squared over 2 plus x cubed over 3, and so on. And term by term differentiation, of this series. Term by term differentiation of this series becomes 1 plus x, okay, plus that's 3x squared, okay, plus, okay, so this is simply x raised to n minus 1. Okay, so if we also check it against this, we will have it to be, since this starts with 1, no, so it seems that we really need not to change this because we really have to, we have to consider, okay, consider that we have a constant here 1. So therefore, that can be handled by setting your n equals 1 so that you'll have x raised to 1 minus 1. So that's x raised to 0. That's a constant. That's a 1. Plus, when n is 2, this is x raised to 2 minus 1. So that's x. Okay, so when x is 3, that's x squared, and so on. So here, this is your derivative in terms of the series, and this is in terms of the summation notation. So again, we don't have to change the limits. Okay. Again, changing the limits depends on the results. Okay. So you really have to look at the first few terms of your derivative before actually jumping into conclusion that you need to change the limits. Okay. So I may have probably missed that point earlier. Because here I have emphasized that there is a change in limits. But this is for the general Okay. And that actually is because you have an A0 here. Okay. And since that A0 already disappeared when you actually take the derivative, that is where you change the limit. Okay. Here, what happened is that at the start, um, your series does not or has a constant. Okay. Your series at the start has a constant. Tama ba? No, it doesn't have a constant. Okay. But in the derivative there is a constant. So you might want to inspect that, okay? And you might want to take a look at that every time you're taking derivatives and integrals, okay? Look at the first few derivatives and if it actually describes your your summation your summation notation. Okay? So that's your derivative. Okay, you were able to get the derivative. And this is your integral. Okay, so again, this is simply found by um, having originally your f of x is the sum of x raised to n plus 1 over, x raised to n over n for n equals 1 up to infinity. If you actually integrate this, the integral of f of x dx is actually the sum of x raised to n plus 1 over n times n plus 1 by the use of the power formula. Okay. So you'll have it from n equals 1 up to infinity. Okay. So you can verify the expansion. Again, verify the expansion, verify the term-wise integration of f of x, and see if this summation, if the summation notation agrees with the term-wise expansion for the integral of f of x. Okay. So you need to do that always. Okay. We try to do that always. Okay. So in this case, we'll proceed now by verifying using the ratio test. By the way, our all of our series seem to be centered at 0. Okay, so we see that f of x, okay, is centered at x equals 0. Okay, so is the integral of f of x dx, okay, and is f prime of x equals 0. So, well, actually, I'll summarize this later. I have a table there. So if this is your number line, if this is your number line, for example, this is your number line. This is the number line for f, the integral of f of x dx. This is the number line for f of x, and this is the number line for f prime of x. So all of them are centered here. Okay, now by ratio test, we will be able to find the radius of convergence and the minimum the minimum radius of interval convergence. Okay. And I would like you to work on this on your own. Okay. This verification that this is the minimum interval of convergence for all of them. Okay. That's the minimum interval of convergence for all of them. Okay. Let me give you one, for example, for f of x. That's the summation of x raised to n over n for n equals 1 up to infinity. Okay. So we'll have an equals x raised to n over n, and its succeeding term is x raised to n plus 1 over n plus 1. So the limit of an plus 1 over an as n approaches infinity equals the limit of an plus 1, the succeeding term is x raised to n plus 1 over n plus 1. And here, the reciprocal of an is n over x raised to n. So we'll find the limit of this as n approaches infinity. Okay, we know for a fact that this and this and this would cancel themselves out, leaving x. Okay, okay, it would leave x there. Okay, so what will be left of is that this becomes, since x here is a constant for this limit because we're evaluating the limit in terms of n. Okay, so that we can actually take it out. So the absolute value of x times the limit of n and n here, leaving n here, would actually be make it positive kasi n naman is a positive integer. So we'll have it as the limit of n over n plus 1 as n approaches infinity, which would lead us to the result of having this limit equal to 1. Okay. Again, if you divide this by n and this n by n, that becomes 1 over 1 plus 1 over n. If you evaluate the limit of that as n approaches infinity, this becomes 0. So what is left of is 1. So this limit is equal to 1. So therefore, by ratio test, okay, your ratio is finite. Okay, it's a finite number, and let's put in some condition for that x so that your series becomes convergent. So that condition is when that absolute value of x is less than 1. Okay, and therefore your series would converge within -1 and +1 as the minimum I o c. Okay. That's for f of x. You can do that for f prime of x and the integral of f of x, and they would all return the same. Okay, so that from the center, we will know that at x equals -1, okay, and x equals 1, okay, your series, these three series would actually converge, okay, within this. The question now is that whether they converge at the endpoints. Okay, so we already have it convergent here at the minimum. Okay, question na lang is at endpoints. Okay, here um we did an inspection of or we did try to determine the convergence at each endpoint for the integral, for f of x, and for the differential. Okay, so observe that all are alternating series. Okay, observe that all are alternating series. We start with the integral. Okay, we use theorem 14 to to determine whether this series is convergent at whether the series is at remember that I already have substituted or replaced x with -1 there. Okay, because I am trying to determine whether this 3 converges at x equals -1. Okay, so by theorem 14, we find whether the succeeding terms are decreasing and if the limit is, or the n term limit is 0. Okay, so both seems to be satisfied. Okay, both seems to be satisfied. Please verify. Okay, and thus your integral of f of x is convergent at x equals 1. So we can confirm now that at this your integral converges here. Okay, so we proceed with the other two. Okay, um, this is this is for your f of x. So at x equals -1, your series becomes this. And this is an alternating harmonic series. This is an alternating harmonic series. So therefore, this is convergent. Okay, so therefore, your f of x is convergent at x equals -1. So this is convergent here. Okay, and finally, for the derivative, we observe that this sorry, that's not it. Ito pala, ito. Okay, so this is this is an alternating series, but this is just alternating between 1 and -1. Okay, which is clearly divergent. Okay, so this is divergent. So as you can see, so if this is divergent, then it excludes this point. Okay, so as you can see, um, on one endpoint, when you differentiated your function, it actually caused your function, or it actually caused the derivative to not be divergent at the endpoint. Okay, while it was maintained in the integral. Okay, this is not generally the case. Okay, but what is sure of is that the convergence at endpoints may differ when you differentiate your function and when you integrate it. Okay, so there are possible changes. Okay, when there are possible changes in the convergence of a series at the endpoints when you differentiate and integrate them. Okay, so we do also do that at the other endpoint. We find the following: this, and this. Obviously, these two are divergent. Okay, these two. This is a positive harmonic series term. So this is divergent. Um, we can confirm that this is convergent using we're looking for convergence, so we cannot use dito. We cannot use theorem 9 because theorem 9 is for divergence, testing whether a series is divergent. Okay. So if you're looking for convergence, that's not the way to go. That's theorem 9 is not the way to go. So we try to find that using the limit comparison test. And that means that I am on, ano ba to? Um, last, last tier of test because I actually have run out of option. I actually, in reality, you can only see that, this solution already here, but in reality, this is not in the book. Okay, if you look at the book, this is not in the book. I actually just wrote this one out. But what you can observe here is that um this limit comparison test was determined after I tried integral. Okay, because again, this is not a geometric series. This is not an alternating series. This is not a this is not a P series. Okay, so um I don't think ratio test and root test will work here because these are not ratio. These are not series that would converge quickly for ratio test, and this does not contain powers of n for the root test. So the only option that I actually had, the first option that I had is the integrate, which did not work. It did not work because I forgot what the reason was, but I think I found a difficulty in integrating it at one point. Okay. I found it difficult to integrate at one point. So I botched this test. Okay. So the only option that I have right now is ratio root test, which is not really consistent with what the form of the AN is. Okay. And that um so therefore, the only option that I have is direct comparison and limit comparison test. I used limit comparison test and I compared it with the P series of this one, which is convergent. Okay. So when I computed the limit of AN over BN, okay, I have this. Okay. Which is 1. Okay. Uh, and in under theorem 13, okay. If that is positive and non-zero, okay, it's either they both diverge or both converge. Okay. And since this is convergent, then it seems that my series is also convergent. Okay. So therefore, I can say that that your integral is convergent at this endpoint. And it is not convergent on f of x and on f prime of x. Okay. So here is a summary, okay, of the results. Okay. And the interval of convergence for each. Okay. So as you can see, there is a change from your original function to the derivative from a convergent series in one endpoint to a divergent one. Okay. And on the other end, okay, a divergent endpoint becomes a divergent power series in one endpoint becomes a convergent series in the integral on that same endpoint. Okay. So these are some of the changes that you can expect. These are not general changes. Okay. I mean, when you take a derivative, a convergent becomes divergent, something like that. No. This is not um in general. Okay. Although they may be valid observations. Okay. What the point is that there will be changes in the convergence or divergence of your series when they are integrated or differentiated. There will be changes. Okay. So there. So in the next lesson, we will now attempt, okay, to use this power series, the idea and operations on the power series like adding them and subtracting them, and of course differentiation and integration to actually generate other power series, so that we can have a power series for your functions. Okay, so the end goal here actually is to have a list of power series for elementary functions. Okay, a list of power series for elementary functions, and use that to generate other power series. Okay, if you can remember, we did that with the Laplace transform. Okay, we had the Laplace transforms of your of your some of your basic functions, and we actually use that in order for us to find the Laplace transform of other functions using that table and the properties of the Laplace transform. So that same approach is what we will try to do here. Okay, using a table, okay, a lookup table, and the properties of your power series, we will be able to expand the lookup table to other functions and write power series equivalent for your um, functions. And also, we will try to answer this question. Kasi what is not yet being answered is that we were able to write a series a function into its power series. Okay, we were able to do that. Okay, but the question and we were able to determine its convergence. So we now know that it can converge at a certain interval. Okay. But what we haven't answered yet is that if this converges, does this sum actually converge to f of x? It, kasi it can converge, but it doesn't necessarily have to follow that it would converge to f of x. Okay, that's the thing. So what we will have to answer on the next lesson is to determine whether that actually converges to f of x. If it converge, does it converge to f of x? So those will be answered in the next two lessons.